Okay, so today's topic 5 lesson, and we're going to discuss some basic concepts of magnetism. And like I said before I began recording the lesson here, today there's no math. We're not going to do any equations. We're also not going to yet discuss the interplay between electricity and magnetism. There is very much, like the electromagnetic force is really two things. We've so far discussed electric forces, electrostatic forces. We're now going to talk about magnets. But on Monday when we do our new lab, you guys are I'm going to ask you to try to discover the relationship between them, and then later I'll actually lecture on it. I'll give you a lesson on it, okay? But today, right now, we're just going to talk about some basic principles of magnets in case for some reason you've never seen a magnet before in your life and you have no idea what it is. We're going to kind of give a little basic theory to it. So no calculations. In a way, today is actually kind of story time with Chris. I'm going to tell you some history. Yeah. Story time with Chris. We're going to talk about some history of magnetism, and yeah. Okay, here we go. You guys can read. The first recorded, at least what I've read. Guys. Fellas. Thanks. Okay. The first recorded observations of, I don't even know that you'd call him a scientist, but of someone who learned about the magnetic properties of magnets is it's a shepherd named Magnes. And I believe that's actually the legend is as to why the word magnetism kind of came to be, is that the shepherd Magnes, he apparently discovered that there was a rock stuck to the nails in his shoes. Now you got to think, like, this was in 800 BC, so we're talking like 800 years before, like, the Common Era, 800 years before Christ, so that's like, what, 2,800 years ago? You're talking about a shepherd who, when they made shoes, they literally used nails to make them. And he discovers, wow, there is a rock stuck to my shoe, and it's not coming off. And that would be kind of weird to notice, right? Because you're like, why is this sticking, right? I imagine he even takes the rock off of his shoe and then goes, oh, and he kind of puts it back again, and it attracts, and it gets stuck to the nail in his shoe, and he goes, whoa, a magnet, magic, right? You know, my 1-year-old likes to play with fridge magnets. And I mean, I think she has the same wonderment as to, ooh, if I put this right here, it goes zip and zaps towards the fridge, right? So let's talk a little bit about what he discovered. He actually discovered an ore, a rock, that is Fe3O4. And I'd like to talk about that for a little bit, because some of you have some chemistry background. And I love talking about the chemistry overlay, Fe3O4. This is a compound that you probably don't talk about in chemistry because it actually doesn't make a lot of sense. Fe3O4. For those of you who've done some chemistry, what's the common charge on oxygen? Do you guys know? Yeah, -2. Which, oh, what am I doing here? -2. Which means that you'd have a net of -8 with all of the oxygens together. And iron has two possible charges. It's either +2 or +3. And if you kind of do the math and try to figure out, well, how do you get an 8 out of a 2 or a 3? You don't. It doesn't work. So if you haven't seen to Fe3O4, it's a really cool compound. Here's how it works. It's actually FeO combined with Fe2O3. It's actually two different iron ore compounds merged together. This one right here is known as iron 2 oxide, if you know your chemistry. And this one over here, I'm running out of room, but it's iron 3 oxide, right, due to the +2 and -2 charge, and the +3 and the -2 charge. And what ends up happening is when you take one iron 2 oxide and one iron 3 oxide and merge it together in like one big superionic compound, how much do you have total? 3 oxygens, or 3 irons and 4 oxygens. So anyways, if you haven't seen that before, that kind of explains, if you're wondering, Chris, how the heck did you get this Fe3O4 compound? But that's actually what this guy discovered, Magnes. He discovered an iron ore compound, and this one's unique because it has magnetic properties. And so for the longest time, magic was often used with things like magnets and forces and fields because people didn't fully understand them, but you could play some pretty cool parlor tricks with them. Eventually, someone discovered something really cool. If you took a small sliver of this magnetized rock and you put it on a little bit of water, it always spun until it pointed the same direction every time. I imagine the first person who tries this, they have like a disc. They put a little sliver of rock, and the rock was pointing this way. And then slowly over time, it starts pointing that way. And then you do the exact same thing again, and you set it up so that it was pointing this way. And over time, it eventually points this way again. And you do it one more time. You're like, no, I'm going to point it in the complete wrong direction. And eventually, it spins itself to pointing this way. And someone discovered that you can actually out of magnets because they always point the same direction. They always point north, effectively. And this is where there's a lot of overlap then between the electrostatic unit and the magnet unit. You guys probably already know this, but in electrostatics we have positive and negative charges, and magnets there are north and south poles. And that's what we designated them as, is it was based on what direction it pointed. And so because it pointed what we called north on a map, they called it the north end of a magnet, right? They'd known about north, south, east, and west before because they had mapping systems all ready to go. But since this rock always pointed north, that's why they called it north. Does that make sense? And then the opposite one always pointed south, so they called it south. Okay. So we can actually draw some field lines and talk about forces behind magnets. One of the things that was also discovered that you probably already know is that north poles attract other north poles but repel south, right? Like things attract each other. No, like things repel each other, opposites attract. So if you were to have a north and a south, they'll attract each other. If you have a north and a north, they repel each other. And you can actually visualize field lines then based on what a typical bar magnet would do. In this bar magnet right here, you can kind of see how there's some field lines that are kind of pointing, in towards north and in towards south, but they're kind of going in a little curved section right here. It's the exact same thing as charges. They work the same way. We'll talk about fields in a little bit here as to how they were defined, but there's a lot of similarities. I doubt this will come up, but in case it ever does, there's actually only certain metals that actually have magnetic properties. There's some metals that they're not magnetic. They just don't work that way. We call them ferromagnetic. You guys know the prefix ferro, what it refers to in chemistry? What is ferric? You ever heard this before? Okay, ferric means iron. You've ever heard of ferrous chloride or ferric chloride? That would be an iron compound. It's the Latin for iron. And so since iron was one of the first things that scientists recognized were magnetic, they called them iron magnetic because iron can be magnetized. We've since discovered that it's not just iron. There's also cobalt, nickel, and gadolinium. And there's more, but those are kind of the main things that we make magnets out of. Aluminum is not magnetic, I believe. Right? There's certain metals that are not magnetic. So I've got a slide right here that kind of discusses the similarities and differences then between the three fields we're going to learn about in this unit. I'll go back here so I'm not in your way again. So the three fields that we're learning about in this unit are gravitational, magnetic, and electric. Okay. And this would be a good chart to kind of illustrate all the similarities and differences. So I'm going to walk through them here. Magnets are very strong. So are electric fields. Magnets and electromagnetic, they're the same force really, but these two things are very strong. Gravitational fields, though, are very weak. I've discussed this already. Why are gravitational fields so weak when it's the only force we notice is gravity? Why do we even notice gravity? Why do we notice gravity? Because the Earth is so massive. Do you notice the gravitational attraction between you and the chair you're sitting on? Do you notice the gravitational attraction between your pencil and the paper? No, because those objects are so small. The only reason why we recognize gravity as being a worthwhile force is because Earth is just so darn big. Okay? So although gravity seems like it's a strong force and field, it really isn't. It's actually very weak. Now, in terms of calculations, the next line right here talks about calculations. We only ever calculate gravitational fields and electric fields. The formula for an electric field, if you guys remember, was either E equals V over D. That was one way you could calculate an electric field. Or you can also calculate it as KQ over R squared. Those are some ways that you can calculate an electric field. We can calculate gravity. Gravity's electric field would be something like big G M over R squared. You might have done that last year in Physics 20. We don't calculate magnetic fields in this course. We just don't. Okay. We will tell you what the magnetic field is, but we only actually calculate them in relation to other forces. So we're not going to focus a lot on math calculations for magnets. The next line right here talks about similarities between how they have different poles, because you have positives and negatives in electrics, so therefore you can attract and repel. You have north and south in magnets, therefore they can attract and repel. But gravitational fields, you only have matter. There's not, well, okay, we're not getting into antimatter yet, but there's only matter, right? And so there's not a positive and a negative in gravity. There's not a north and a south in gravity. There's just two objects. So these have north and south. These have positive and negative. You can't even see that. And this one right here, though, it's the same thing. The next line right here talks about similarities and differences between what's involved. There is a direct relationship between the magnet that's involved. Gravitational fields, there is a direct relationship with the masses involved, which explains why when Earth gets big, we notice gravity. There's even more gravity on Jupiter, because Jupiter's even larger. There's less gravity on the moon, because the moon's smaller, mass-wise, right? Same thing here with electric fields. If you have larger charges, there's a direct relationship. Last box on here, kind of comparing things. You can separate two masses that are two charges that are electrostatically attracted. But this is kind of an interesting one. Scientists have never been able to separate two poles of a magnet from each other. If you guys haven't ever heard or seen this before, imagine you have a magnet, just a basic bar magnet, and you have a north-south. And let's say it breaks and you cut it in half. It actually makes two smaller magnets. It makes this into a new north and south, and it makes this into a new north and south. And you now have two smaller magnets. And scientists are actually trying to create what's known as a monopole. There are actually like current scientific efforts trying to basically create a magnet where all you have is a north and all you have is a south. But they haven't been able to, at least as of the last time I checked. So that was last semester. So unless someone's winning a Nobel Prize for it this upcoming year, as far as I understand, yeah, you can't have just a north or just a south. They always come in pairs. But you can have a positive and a negative and then separate them. Does that make sense? So here's some pictures of some different types of magnets, just in case you've never seen a magnet before in your life. Let's talk about these ones here. This one right here is a classic bar magnet. Usually what happens is one side is north and the other side is south. Did we have to call them north and south? Couldn't we have called them side A and B, or cat and dog, or positive and negative? Historically, why were they called north and south? It's the direction that they pointed when they put them on water. It's the only reason why we gave them those names. Right? The names themselves, north and south, are relatively arbitrary, aren't they? They're just words. The only reason we gave them those designations is due to how they spun on water. North pointed towards north, so they called it north. Let's talk about this magnet right here. This is a horseshoe magnet. The way it works is that one of these like prongs right here is, say, north, and the other side is south. And what's cool is that the magnetic field is actually strongest right between them right there. That's actually that's the strongest point of the magnet, because they're actually super close to each other right there. But they are actually linked via this like horseshoe shape. So that's the name for this one. This is called a horseshoe magnet. Horseshoe. This is just a basic button magnet. And some kids might suggest, Chris, why can't this just be a north magnet? Anybody know how this magnet works? Where's if this is north right here, where's the south to it? On the other side, yeah. Like the top is north and the bottom is south. Each side of the magnet, as you like flip it like a button around, like a coin, each side, like the head's side is north, the tail side is south, if you treat it like a quarter. So all magnets have to have a north and south pole. Again, north and south are arbitrary words. We just use them based on which way they pointed. But, I mean, they have a side A and they have a side B. Here's a slide that kind of describes a few different concepts here. The first, I have a little blurb talking about monopoles. As far as I know, and again, if someone discovered a monopole, like instant Nobel Prize, I'm sure. So since the Nobel Prize wasn't discovered for this yet. But no one's been able to cut a magnet in half and make a single pole, which is distinct from the other fields. It's very unique. You can separate a positive and a negative charge. You can separate masses that are gravitationally attracted. You cannot separate a north and south pole. You just make new ones if you do that. And here's the reason why. It's called domain theory. This is the idea as to why this occurs. And this is a theory still. I need to point that out because scientists really don't have the ability to go and like look at why particles are magnetic. It's not like we can hop on the magic school bus, zip down to size, and go look at what's happening. There are no particles that are like something we... Here, this is the idea. It's actually induction. What they believe happens is that all of these little pieces of metal, they're split into what's known as a domain. And so each of these little chunks right here is all like, say, iron. This is a small little chunk of iron. Here's another chunk of iron. Here's another little chunk of iron. And all these little pieces are called domains. And normally, they kind of have like an orientation where like they kind of just go a little bit here, there, and everywhere. They're kind of random, okay, in terms of the orientation. However, when they are magnetized or put in a magnetic field, the orientations all align in the same direction. And the theory is that each of these little pieces here, they're all small little magnetized pieces. Like this is a north and south pole of a magnet here. And there's a little north and south pole here. And there's a little bitty north and south pole here. And there's a little bitty north and south pole here. And collectively, because they kind of all are scattered in random directions, we don't notice that this whole thing is magnetized. However, if they all go in the same row, and so this has a north-south here, and another north-south here, and another north-south here, and another north-south here, and everything is perfectly aligned. Do I have that word? Here it is. If everything's perfectly aligned, the logic is then you have one big powerful magnet that's really, the big powerful magnet is really just the combination of a bunch of little bitty pieces that have finally all been lined up. That's the logic behind it. They call that domain theory. Does that make sense? So I like this slide best because I think this kind of illustrates what I'm going for here. Imagine you have just a random piece of metal, and this piece of metal is non-magnetized. You can almost treat the piece of metal as though inside of it there's a whole bunch of different north and south poles. And again, a north and south pole isn't something tangible that you can actually go and like remove, because you can't just remove the north pole, because when you remove the north pole you also remove a south pole. So we really can't test this in a traditional way. But the idea is that in a big piece of metal you have all of these different poles that are lining up. Some of you guys have done chemistry. You guys have learned about how like water, I'm going to use another example here, about how water, if you draw a water molecule, how this side right here is slightly positive, this is slightly negative, that's slightly positive. Any of you guys ever seen that before in a chemistry class? How water is polarized? We can explain water's polarity because we understand electrons are the cause of that if you know how chemistry works. The reason why is that hydrogen has an electronegativity of 2.2 and oxygen's electronegativity is 3.4. And because of that, the electrons spend more time near oxygen, and it causes a pole to occur. So we understand polarity when it comes to electrostatics, but we don't fully understand polarity when it comes to magnets because we don't know what's causing it really. We just know that it exists. So long story short, all of the pieces of metal, we believe them to be like non-aligned, but in a magnet they are all nice and neat in desks, in a row, facing forward, you know, and that's what makes something magnetized. Which then explains why if you cut a magnet in half, see how this side right here must be your north side, and this side would have been your south side? But if you cut a magnet in half, well, the last thing you had on this side right here was all of the souths, and the last thing you had before you cut it in half right here was all your norths. Now it explains why you're getting two magnets when you cleave it in half. Again, it's the best theory we have. It's called domain theory. Okay, changing gears a little bit here. I want to talk then about the field that magnets create. We're not going to do a lot of calculations with magnets. Unlike gravitational and electric fields, we don't actually do magnetic fields, other than just talking about what their symbol is. And so this is unfortunate, but the symbol for magnetic field has now been defined as letter B. And the reason why they went with letter B is that before we went with letter B, there were way too many different definitions for magnets. Remember how I told you guys how we had the wrong definition for electricity for the longest time? Ben Franklin thought that positives were moved, but then we realized that negatives moved. But then it kind of became hard to like change science because everyone had kind of worked with one way for so long that it became hard to change that. This would be a good example of scientists recognizing there are too many ways of measuring magnets. Let's all get on the same page, people, if that makes sense. Because for the longest time, they had way too many different ways of measuring. Down here on the bottom, I have all of the different ways that scientists had to try to measure magnetism. And it is crazy. When I went through school, I learned about this thing right here. It was called a Weber, WB. It was one of the ways that we tried to measure magnetism. For the life of me, I don't even know what H stands for. But it was another way that scientists had to measure magnetism. You could also measure it in volts times seconds over meters. What I'm trying to get at here is eventually scientists recognized, guys, you can't measure magnetism this way, and you measure it this way, and you measure it this way. We should all have the same letter and the same unit. You get what I'm saying here? They finally said, enough is enough. Get on the same page, people. So the symbol that we use is B, and the unit is T, which was named in honor of Tesla. Okay. So I need you guys to make sure you're aware of the difference between these here. The symbol B, sorry, that's the worst B ever. Let's do that again. B is the symbol that we're going to use for it, and we're going to measure it in Teslas. But as you can see on this little bottom slide right here, Teslas used to be measured in all of these different unit types, and it was just too crazy. Measuring things in Webers per meter squared was too challenging. So we just said, let's just go with this. Call it a day. Tesla didn't have anything named after him at this point. We've named something after Newton and Coulomb and all the other scientists. Joule, they got a name. Why didn't we name something after Tesla? So, okay, let's name it after Tesla now. Does that make sense? Here's a frame of reference, by the way, if you want to talk about how strong a field is for magnets. Earth actually has a very weak magnetic field, believe it or not. The only reason we notice it is because Earth is so large. But really, Earth actually has a very weak magnetic field, only like 5 to the negative, 5 to the negative 5 Teslas. A fringe magnet is actually stronger than Earth's magnetic field. One of the good lab magnets could be 5 Teslas. And if you had went to the surface of the sun, like a star, it might be like 1 times 10 to the 8 or 9 Teslas. So those are some frames of reference in case you're wondering how strong different fields are. But Earth does emit a magnetic field, but it's really small. Some more definitions. Sometimes we have permanent magnets, sometimes we have temporary magnets. There are some magnets that you can re-magnetize. There are some magnets that only work once in a while, and we're going to discuss this later, but there are certain magnets that you can actually switch on or off. We have a name for them. We call them electromagnets. And we're going to discuss that in a future lesson. But it actually is the relationship now between electric theory and magnetic theory, the idea that you can actually make a magnet out of electricity. So, a few other minor notes here. These aren't really the most important things to know, but just little details. If you ever drop or strike a magnet with a hammer, it can actually screw up the alignments of domains. And so drop a magnet too many times, and it becomes demagnetized. All of those domains that were all nice and neat in a row, they eventually kind of scramble a little bit. The last thing you might want to know here is that magnets, you can actually heat them up and screw it up as well. Because if you add energy, electrons move too fast. And you can actually demagnetize a magnet by heating it to a certain temperature. So if you want a magnet to stop working, heat it up. Okay, I got to keep moving here because I wanted to give you guys some time to work still. Here's something that we actually need to use and apply. Okay. You know how when we had fields in electrostatics, we just kind of had to choose whether to base it on positives or negatives, and we said we're going to define a field based on what positives would do? Well, kind of have the same thing with magnetic fields. We're going to base a magnetic field based on what a north would do. So a magnetic field line is always drawn towards the south and away from the north. And that's just the convention we went with. So every time you draw these sorts of lines, draw your arrows towards south. So right here, can you see how the field is pointing away from the north end of the magnet? Because wouldn't a north magnet want to get away from a north magnet? And wouldn't over here a north magnet want to come towards a south magnet? So that's how you draw field lines. Draw it towards the south. I'd like to actually go back, if I could, in the slides here, and find a picture that I had earlier. It was this one right here. I briefly was talking about fields right here. I want to label it a little bit better now then. I can actually draw the arrows going here. The arrows would be going this way. They'd be going towards the south and away from the north. And that's just the convention we went with. We had like two choices. You either draw the lines towards north or away from north. Decided to go away from north. Okay, fair enough. The logic was, let's base it on what a compass does. Here's another picture that kind of illustrates the same thing then. Say you have two bar magnets here, and you've got a north-south magnet, you've got a north-south magnet right here. Then the direction of the field would be away from this north magnet towards the south magnet. But here's the cool thing. This is very similar to voltage then. Remember how in voltage we had like a plate that was negatively charged and a plate that was positively charged? And we could draw some field lines between them. Which way do we draw field lines when we're drawing electrostatic? Based on what a positive would do, so a positive would go towards the negative. In a way, it's very similar. This diagram right here, where you have field lines going from north to south, is very similar to this diagram here, where you have field lines going from positive to negative. But I want to make sure I illustrate something here. North is not the same thing as positive, and south is not the same thing as negative. Okay? They are different from each other. Positive and negatives are charges. They're actual tangible objects that have mass and have charge that we can work with. Positive and negative poles, north and south poles, they don't really work in the same way. So don't assume that just because your field lines always start at north and always start at positive, that north is positive. They are still different from each other. And yet related. We're going to get to the related part next week, though. Here's some more pictures that kind of illustrate the same sorts of things. So it's just showing you the field lines. So I'm just going to draw on a couple of arrows real quick. The arrows would be pointing towards the south here. They'd be pointing towards the south here. They'd be pointing towards the south here. You'd actually have kind of a gap in the middle here, hey? Because although we're not going to put a particle here to get suspended, the lines are pointing away from the north, trying to point towards the south. And so you actually would have a location in the middle here where you kind of don't have any field, because the field is like being repelled away in all directions. Any questions so far? Okay, cool. We're almost done here. The last thing I want to discuss then is, like I said, more story time with Chris. Remember how we defined north to be the direction that the compass needle pointed? I want to refer to that again here. Back, 2,000 years ago, if you had a map, they knew that north, south, east, and west, they knew the directions that they were, right? And then someone realized, hey, I can make a compass that tells me what direction things are, because you put a disc of water on there, and you have a magnet point towards, and the magnet always pointed towards north, and so they said, hey, this better be the north end of the magnet. That made sense, right? Magnets point north. But hang on a sec here. Shouldn't a north side of a magnet be attracted to the south pole, right? Don't norths get attracted to south? This is another example of how we kind of screwed things up, and now conventions really can't be fixed. Our north pole geographically south, magnetically south. It's like super confusing. It makes no sense. But let me see if I can explain it over the next few slides. I got a ton of pictures here. This right here is what we consider to be the geographic North Pole. Okay. And so we often say that this right here, this location is the geographic North Pole. And the reason why we say that is because this is the location that does not spin. You guys know how like the Earth spins on its axis? Earth kind of spins around on its axis, and the geographic north and south poles are the locations upon like the pivot upon which Earth rotates. The weird thing is that the magnetic poles are actually not where the geographic poles are. They're actually in a different spot. And furthermore, this actually shouldn't be considered the magnetic North Pole. It should be considered the south magnetic pole. The reason why this should be considered the south magnetic pole is because if the north side of a compass points north, it's actually pointing at the south pole, because north things are attracted to souths. And that's what I have written on this slide right here. There's a few like misconceptions that I wish we could go back and just like fix and change so that kids don't get confused. So the first one is the difference between a magnetic pole and a geographic pole. Geographic poles are where the Earth spins, but that's actually not where the magnet inside of the Earth lies. There's actually like over 1,500 kilometers difference between them. The other note that I have here, though, hopefully this is starting to make sense here. If a compass is supposed to point towards the north, then it's actually pointing south, which means that, like, okay, where's the West Side Bridge here? I think. So Whoop Up is going that way, right? So that would make this west. Does that make sense? Because Whoop Up is running this way here. Is that right? Hang on, am I doing this wrong here? Yeah, this would be west over here, wouldn't it? Because wouldn't this, because Whoop Up is right there, is it not? Parking lot's over there. But doesn't Whoop Up go doesn't Whoop Up go east west? Yeah, so Whoop Up goes east west. Yeah, okay. So Whoop Up goes east west. This street right here is that. So just to make sure we're all on the same bearings here, that would be west. That would be east. So if that's west, that's east, then north, south. We all in agreement? So just to make things simple, let's just make this way be north. It's not north. This is what makes this stupid, is that if I had a compass, the north end of a compass needle is going to point that way. But it actually is pointing to what we would call magnetic south, because norths are attracted to souths. And it's all because when they first named things, they said, hey, this thing is pointing north, let's call it the North Needle. Let me say that again. They said, hey, this thing is pointing north, let's call it the North Needle. Why was it pointing north? Because it's attracted to the south. They should have actually, when they first did this, they should have named them oppositely. So if this starts to make sense to you, I have a bunch of pictures to end our lesson here. Kids hate this when I explain this thing here, because it throws everything off here. Okay. First, I have a slide here that actually tracks the magnetic poles have actually been moving over time. I found this slide online that talks about how this is where the geographic North Pole is, because that's where the Earth spins, and then the magnetic pole is actually, it's been moving over time. It used to be over here, and it's slowly but surely been migrating, actually moving slowly but surely over time, which is kind of weird. Here I have a slide that talks about the same thing. Right here is where the actual South Pole is. It's in the middle of Antarctica. But the magnetic pole is right here. But almost all of these diagrams are actually labeled incorrectly. This is actually not magnetic south. This is actually magnetic north. Because the south end of a magnet points towards the South Pole, but if we're calling it the South Pole and south is pointing to it, it actually was north. Why couldn't we figure this out and just make it proper? You get the frustration here? It's the same thing as conventional current. Why don't I just go to the last slide I've got right here? This is probably the best one. I'm going to go to this one first, and then I'll come back to the ones I skipped. This is a slide that actually truly describes things with the proper vocabulary. This right here is geographic north. Okay. Geographic north, like this is where Santa lives when you talk about that with my little children. This is where Santa lives, the geographic North Pole. Okay, and the reason why it was geographically north is that thousands of years ago, they decided to go, well, that way's north, south, east, and west, right? Made a convention, right? Now that all the maps in the world have been written with the convention, north, we said north was this way, right? North, south, east, and west. Once all the maps in the world have now been printed with this convention, we can't fix them anymore, right? They're locked into place, we can't change that. So north was defined as that way. Then someone came along and said, hey, a magnet also points that way. Let's call this direction north as well. But then the problem is norths are actually supposed to be attracted to souths. And so what ends up happening is the magnetic south top of the Earth, it's not even in the same place as geographic north because it's been moving over time. And so whenever we talk about that direction being north, it's actually magnetically south, but geographically north. Why? But we can't fix it anymore. You get the reason why we can't fix it? Because we should be calling this south, but since every single map made for the last 3,000 years has said that that way is north, it's got to kind of stick that way. And because we defined magnets as having a north and south pole based on that, it kind of screws things up. Same thing down here. At the bottom of the Earth is what we now call geographically the South Pole. But it actually is over here somewhere is where the magnetic North Pole is, which then explains why the south end of a compass gets attracted towards this. So this is such a confusing, dumb topic here, but hopefully that makes sense. I got a few more things to kind of illustrate here, and then I'll wrap up here. Here's a picture of the Earth. Earth spins on its axis, but technically the top of the Earth, somewhere inside the Earth, all of those domains are lining up. And they're lining up in such a way that the south domains are actually at the top of the Earth, and the north domains are at the bottom of the Earth. And if you stand right here with the compass points that way, but it's actually pointing to geographic north, magnetic south. And they're actually in like slightly different spots. They're actually not in the same location. Here's another picture that kind of shows the same thing, only this one hasn't been doing it properly. This is a picture that's actually labeled incorrectly. The geographic North Pole is right here. No, I take that back. The geographic North Pole is right here and right here because that's what it spins on. But the magnet inside the Earth should actually be a south right here and a north right here. So now we have two things in this unit. We have the fact that there's conventional current and electrical current, which are backwards. And it's like, why can't we just pick one? Well, once they started doing it wrong for a couple hundred years, it's kind of hard to like fix that. We have the same thing with magnetic and geographic north and south. So one more time to recap, then I'll be done for the day here. We have defined as humans, that way is north, that way is south, that way is east, that way is west, right? That's what we defined it as. Thousands of years ago, every single map in the world is defined with the same things there, right? The guy comes along, finds this little spinny rock on a compass and goes, hey, it's always pointing that way, right? And if I turn it a little bit, no, it always pointed that way. I'm going to turn the compass, it always went back to that way. And so a person says, hey, I'm going to call this side of the rock north because it always points north. And now we realize that, hang on a sec here, north things are actually attracted to south. What they should have done is they should have said that if that way is north, they should have said that the other side of the compass needle, they should have said that one's north. But once we got the convention going, it screwed things up, and it's still screwed up to this day. You can even see all the pictures that I found online. Half of them are done right, and half of them are done wrong, depending on whether you actually get the concept of geographic versus magnetic. So, okay, that's my lesson. Story time with Chris. So here's what we accomplished. Hopefully you learned a little bit about how everything is wrong in the world, and geographic and magnetic north and south are all screwed up, and this is stupid. I agree, it is. It's kind of fun to talk about, but it is stupid. We talked a bit about magnetic theory, and we really don't know what's going on. We can't actually like look at these particles and figure out what's going on there because it's not like there's charges on them. We seem to think that there are domains that line up, and if everybody points the same direction, I think that's why it's magnetized. It also explains why if you cut it in half, hole yet. We talked about how the field is represented by the letter B and the unit T, but it didn't used to be this way. They used to have all sorts of units for magnetic fields, and eventually they finally said, okay, there's too many things in the scientific world that are non-uniform. Let's just stick with one thing, people. And so we just need to know that Tesla is the unit we use for field strength. You need to know that a field is defined as always pointing from north to south. So to pick a convention, they just said it's always going to be north to south. Stick with it for the rest of time. Okay. And I think that's more or less the main highlights. So, what questions do you guys have? None? Really? After I just told you that north is south and south is north and everything in the world is wrong, you have no questions. You guys good? Okay, cool.